and it has to be the y derivative of negative n. So we have negative ny, but we have the negative of that because it's the negative y derivative. The y derivative of the coefficient of dx is the y derivative of negative n. We got another y. We have another negative from this relationship. And by Green's theorem, whatever comes in front of dy, whatever the coefficient of dy, appears over here as an x derivative. Okay, the sign is the same. So what appears here with dy? M. So what we're going to have over here is the x derivative of whatever's in front of dy. In this case, it's m. So we have plus mx. So that when we apply the two negatives, this integral becomes this, and this mx plus ny is just the x derivative of our original m function, defines f, and the y derivative of our original n. That is, this expression is just the divergence of our f function. Remember, divergence is the partial with respect to xi plus partial with respect to yj dotted with the f function. If this is our f function over here, then clearly the divergence of that function is mx plus ny. And just to make a finer point on that, divergence of f is divergence, the del operator, dotted with our function, and that gives us partial with respect to x of m, which is mx, plus a partial with respect to y of n, ny. So that this is the divergence of f dotted with, or divergence of f, and it's not dotted, it's multiplied by dA. So what have we established? Well, we've established that the integral of f dot n ds is equal to this, which is equal to this integral, which is the integral of the divergence of f dot dA, so that the integral over c of the normal component of our vector field along a closed curve, and I haven't written that as a closed curve, I have to go back and clean up the notation. The integral of over a closed curve of f dot n ds is then equal to the integral over the region enclosed by the curve of the divergence of f integrated over the area. This is in itself a really pretty neat result, and when we extend it to 3 dimensions, it's going to be even neater. As I mentioned, I've been a little careless writing my integrals over the curve C. As a matter of fact, I see a place here where I didn't even write the C. And I think I've gone through and cleaned that up. If that was bothering you, it's to your credit. Quick summary, unit normal to our path C with parameterization is this. We multiply that by ds to get our n ds, which is just this. Our f dot n ds then is this, mi plus nj times dotted with this vector, which in a very straightforward manner gives us this. And now if we kind of turn our understanding of Green's theorem around with the notation, in other words, if we express Green's theorem in terms of coefficients of dy and dx as stated up here, the notation changes a little bit down here, and we get this, which is just the integral of the divergence of f dot dA, establishing the divergence theorem in the plane, that the integral over a closed curve of f dot n ds is the integral over the area integral over the enclosed region of the divergence of f. You'll recall that a little bit earlier we looked at a vector field that maybe looked something like this, diverging from a point, or the opposite, converging on a point, which would be a negative divergence. If we integrate either of these around a closed curve, we see that the normal component of these vectors, that all these vectors tend to have a normal component, a component perpendicular to the curve and outward, so that when we do the integral, we're going to get a positive result, or in this case, a negative result, but we're not going to have the situation where our vector field pretty much follows the curve with no normal component. So when we have a strong normal component around any curve, that means we've got a divergence within that region, and if we integrate the divergence over the area, we get the integral around the curve of the normal component of the vector field.